This is a perfect, since this is probably going to be a linear relationship between the 30 degrees and 110 degrees and the 1764 and 1336, it should be a straight line between those two points. So let's see if we can draw something up and see if we can figure out this formula. Okay, so the slope-intercept formula is y is equal to mx plus b. Okay, b is going to be an offset. The m is the actual slope itself. M is equal to the slope, which is equal to the rise over run, which is also equal to the delta y over the delta x. And all that means is 2 y positions and 2 x positions. So you have a line that has, a line is always going to have 2 points, and they're going to have 2 y's and 2 x's, or xy and then xy. So let's go ahead and take a look at a little graph. We should probably draw a graph and kind of understand what we're doing here. So let's say that this is temperature on this and on the y-axis, and the x-axis will be the digital voltage values. Okay, so let's take a look at the different values. Let's say that this is the 30 degree mark, and this is the 110 degree mark. And you're going to find this very interesting here, because you'd think that in the temperature sensing you'd have the high value as the 110, but really it's the low value. So right here was, what was the number? Okay, it's 1336. That's the 110. So if you draw a line, we have our first point here, and then the other extreme is the 1764, which is our 30 degree mark. So we could actually just draw a line from here to here. And somewhere along this line is our actual temperature digital value. And you know it was somewhere around 1728 of 1727. So let's just say that that's somewhere around here. So where that meets here, that would be where that temperature is. We don't know what that temperature is, but we're going to figure that out using the slope-intercept formula. So let's find out what the slope is first. So first we're going to take the difference of the y values. And the y values in this case is the temperature. So it's the difference in the temperature. So the difference in temperature is equal to 110 minus 30, which I know this is actually correct. This was correct in the data sheet. So this was actually shown in the data sheet. So this value would be 80, right? Yeah. So we have our delta y. So our delta x is equal to the delta of it's actually the V30 minus the well, let's just call these voltages. The delta of the voltages, which is equal to the V30, which is this one right here. And this would be V110. Okay, so the answer to that would be 1764 minus the 1336. And that would be equal to 428. So then our slope will be equal to 80 over 428, which is equal to, I'm actually going to flip this around because I want to have a value more in line with the specifications in the data sheet, which is around 4.3. And that just means that I'm making this part the temperature. I'm just going to put that on the x-axis, and then the digital voltage would be on the y-axis. And that's just essentially me just rotating the graph around 90 degrees. So I'm going to make it 428 divided by 80. And that's going to be equal to 5.35. So for each degree of temperature between 30 and 110, there is a change of 5.35. So if we took 500, if we took the if we divided it, this particular axis, and each one of these is 5.35 width apart, you'd have, and that would be each degree. This would be 1 degree. 1 degree would be 5.35 on that scale. So now you know we can take the 1764 number right here and the actual data that we're getting from the temperature, and we can get the difference between 1764 and that temperature reading and determine what degree it is. Because we have the number of degrees, we can divide that by 5.35. Another way to think about this is we're going over 5.35 and we're going up 1 degree. Going over 5.35 and we're going up 1 degree. If we did this the other way, like 80 over 428, let's see what that would equal. We get a value of 0.1869. So for each change in this number here, like this between 1764 and 1763, that would be 0.1869 degrees. That might actually be a little bit easier to determine. And the reason why I'm trying to figure this out is because I'd have to do extra work to find out where this crosses the axis and where this one crosses the axis. Because we need to know where those cross the axis for the slope-intercept formula. And we really don't need to know that because we have what is a particular degree. So let's say we take the 1764 and subtract it with the 1727. So let's see what we get. So that would be 7, 14. So that would be 37 point difference. So if I multiplied 37 by 0.1869, that would equal the number, the amount of degrees Celsius. And that would equal 6.9153 degrees difference between the 1764 and the 1727. So if the 1764 is 30 degrees, and we added the 6.91, let's put it next to it. So let's plus 30 degrees to this. So that would be 36.9153 degrees. And that sounds like a reasonable temperature for my microcontroller in the, or within its environment. So I think at this point we have enough information to write our code. We know how to determine the slope, which is just subtracting the V30 and the V110 and subtracting the actual temperatures and figuring out what that slope is. In this case it's 0.1869, and it actually has some more precision after that. So we'll add those into the program. And then you can just take the difference from the 30 to the actual reading and then add 30 to it. You should have your temperature. So let's go ahead and start programming and see if this works. So first let's see if we can calculate a slope. We don't actually have to do that within our while loop. Our slope is always going to be set no matter what. That doesn't have to be recalculated over and over again. So let's find out our slope, and we're going to make this a float. We'll call it slope. In fact, the data sheet calls it average slope, so we'll call it, I think it's called average slope. I'm just going to call it slope. So this is going to be equal to the difference in temperature, which is going to be 80. Now let's go ahead and do the 110 minus 30 just to be a little bit more verbose. And then we're going to divide that by the change in, or the difference between the voltage at 30 and the voltage at 110. So the voltage at 30 was 17, no, I'm sorry, what am I doing? I should be using the actual numbers in the, so let's start with the 110, no, the 30, because that was the bigger number. So we don't have to do an absolute value. And we're going to subtract that with the 110. So this should be our slope. Let's go ahead and see if we get the correct number. So I'm going to go ahead and just delete all this. And we'll call it slope. And how many? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so we have 10 digits we can display. So we're going to take one of these out since we don't need those numbers. We're going to change this to a 10, and we're going to display our slope, but we need to do it with a float. And we're just going to do this as a new line. Floating point number. Okay, so this is going to be slope, and it's going to be 10 characters. And let's see, what 6. Position number 6 on the second line. Okay, so let's see what our slope is. Hopefully we did it right. Actually, we don't have to keep showing this either, because it's always going to be a constant. So we'll just show it from up here, and this has to be inside the while loop because it's always grabbing the data from the controller. And I believe when I'm dividing two numbers, I have to be very explicit with my casts, meaning that I have to sort of declare what this number is going to be, and I have to declare what this number is going to be. And in this case, I'm going to declare them as a float. I guess there's a couple ways I could do this, and I can do this with variables, but let's go ahead and do it with this way first. So what I'm essentially doing is I'm telling the compiler what this number is going to be, and it's going to be a float, even though it really isn't going to be a float, but I want it to be a float because it's going to end up being a float anyway. So I want to keep all of the casts consistent. And this one also will be a float, even though it's just the number 80. So let's go ahead and try this and see if it works. And you can see that it does work. It looks like I can take away all these X's, so I'm just going to do that. Since we don't have to have those artifact X's on the display. Okay, so now that we have our number, we have our slope, we can go ahead and calculate the final number. Because all we're going to be doing is taking our slope and we're going to multiply the difference. So we have our slope here. We can use it over here at least. We'll call it temperature. And that's going to be equal to the slope times the difference between our calibrated 30-degree temperature digital value, and we're going to subtract the ADC value of the temperature. So that's going to give the difference between from 30 degrees to the value of what the temperature is right now. So we're just finding what's the difference between those two, and we're multiplying the slope to find out what the degree difference is. So then what we can do is we can add 30 to this. Let's go ahead and make sure that order of operations are done correctly, because I want this slope to be multiplied by the difference here first, and then 30 is added to the end. So let's go ahead and see if we get the correct temperature. And we're going to want to, let's see here, we're going to want the floating point number here instead. So we're going to be displaying a floating point number, and let's go ahead and give it 10 digits as well. So let's see what happens. No errors. Let's go ahead and flash the microcontroller. We should have around 36 degrees, and that's good. Looks like it works. So in conclusion, you can see how relatively easy it was to come up with a slope that would give us the number of degrees per point of differing temperature digital value, and how easy it was to actually put that into practice, where we take the actual digital value subtracted by the lowest temp calibrated value, and we multiplied that by the slope, which is the per point difference degree in temperature, and we just added it to the 30 because we're offsetting it up. Otherwise we would have just gotten a 6-degree temperature, which would be completely incorrect, and we're using the calibrated 30-degree temperature, so we had to offset it up to 30 degrees. And all we did was print it to the display and to see what value we got. And you can also see that the difference with what was actually shown in the reference manual, where I think this was done correctly, and in the reference manual in their code example, this was helpful. And this allowed me to figure out what these numbers were, because they weren't really very well described. And looking at the actual technical specifications and data sheet of the microcontroller, and that's one of the reasons why you really should become very familiar with the data sheets. Even though they may be incorrect in a lot of places, it's good to get that information and understand how to look for things, because you can find things, even though it's not correct, you'll eventually be able to find out how to use it. This part, the calibration and the apply, not really sure why they're using these 300 and the 330 and the 300, and how they're using it, because first they're taking the raw data and they're multiplying it by the division between these two, and then they're subtracting the temperature from that. I mean, this to me, I mean, it looks like they're trying to do. It looks like they're trying to find the slope here, but having it multiplied first and then getting the slope seems kind of backwards to me. But this really kind of threw me off. And also looking at this formula here, still doesn't seem correct, because you can see that they're dividing the vsense, which is really the data. I'm not sure where this 4095 comes into play, but the vsense, let's just say that's the data there, that looks correct according to what we're doing here. This would be the vsense, I guess. It has nothing to do with dividing it by 4096 and getting the value of the 30-degree calibration temperature, but we're multiplying the slope by that. And that makes sense to me, because slope multiplied by the x value plus the offset seems correct, because this is more like a slope-intercept formula. This would be y, the temperature would be y equals m, which is the slope, times the x, which is the raw data, minus the calibrated temperature at 30 degrees, the value at least, which is, this would be the X right here. And the Y difference, the Y would be the temperature. Somewhere on Y, this would be the actual temperature. And then you're moving it up 30 points. This is the offset. And when I was using the formula they were using here, actually the temperature code example, I was getting values of in the 60s, and I was also getting values in the 20s, depending on my sample rate. And I knew that couldn't be correct. And I was even wondering, are other people doing the same thing on the internet? And I looked at other people's code, and they were using this code example verbatim. And they must not be getting the correct values unless they have something else going on. Or maybe I didn't write this, maybe I didn't apply this correctly, but I think I did a copy and paste and I just applied it directly. You know, putting this above my, where it's supposed to be, and adding this into the loop. There's no reason why I should have gotten an erroneous data, and I just really can't get my head around how they did this formula and why they did the formula in this way. And it differs so much to the formula they have in the other part of the reference manual. So I guess the moral to this story is, don't always trust the reference manual to be correct, and always verify whatever you're doing in code, verify it according to what you'd expect it to be. Hopefully that helps. Thank you for watching.